Hello engineers, welcome to the last video in the design pattern series. In this video, we're going to look at the interpreter pattern. I hope you're ready. Let's get started. So this is the intent. Given a language, define a representation for its grammar along with an interpreter that uses the representation to interpret sentences in the language, right? So this pattern is mainly used for defining grammar rules and then making use of those grammar rules to solve some particular problem, right? So let's try to understand this with an example. Let's take an example of math expressions. So let's say we have an example like this, 5 plus 10 minus 3. Now we need to evaluate this expression. So how do we do this? So let's first identify the individual pieces. First we have a 5 and then we have a 3. We have a plus, we have a minus, we have open bracket, we have close bracket. So let's say these are our elements in our language. So we need to give them some definitions and some rules. So let's try to give them. First, let's look at the numerical expressions. So we have 5, we have 3. So both of these are numbers. So they have some numerical representation. And then we have addition, which is a different representation. And then this is subtraction. And then the brackets are used for grouping. Let's say they are responsible for grouping an operation. Right? So how do we define rules for such a interpretation? So first we have the numerical expression. Let's say we have any. So how do we interpret it? So how do we interpret it? We just treat it as it is. So 5 will be treated as the number 5. 3 will be treated as the number 3. So there is nothing else to interpret here. So they will be interpreted as is. Now let's talk about addition. So how do we interpret addition? Addition will take two things, a left operand and a right operand. So these are the inputs to the addition. And then how do we interpret it? We interpret this by doing left plus right. Right? So this will be the rule for the addition. Similarly, you can imagine for subtraction, it will also take in a left operand, a right operand, and the operator is subtraction. So the interpretation will be left minus right. Right? So these are the rules of the grammar. So this is the whole idea behind the interpreter pattern. So we define some rules like this and we define some method to interpret it. So in the first case, how did we interpret it? 5 will be interpreted as is, 3 will be interpreted as is, and that is the rule of this class. So what is the rule for addition? Addition will take left, addition will take right, and the interpretation is to add them up. Subtraction will take left, subtraction will take right, and the interpretation will be to subtract them left minus right, right? So these are some of the rules. So imagine if there is a bigger grammar, there will be more rules like this, but the idea is to form a rule, take some inputs, and create a method called interpret, which will actually interpret what that expression is or what that little piece of the grammar is. Right? So that's the idea behind the interpreter pattern. So we can see the usage of this interpreter pattern in many cases. So the first example is math expressions, which we discussed. And next example is SQL query builders. So SQL query systems have a lot of rules. So the select query will have its own particular rules. We have a different rule set for insert. We have different rule set for update and delete. And if you talk about DDL, we have rules for alter, create table, delete table, and so on, right? There are many rules and the queries can be quite dynamic. Select query can be a simple select star query to a complex join query with multiple tables and so on, right? So when we have multiple rules like this, we can create a grammar for that language and then give some interpreter methods for each of those little expressions, and then they can take care of interpreting them and we can build a complex query language like this, right? Similarly, we can see the usage in regex evaluators. So regex are regular expressions which are used for pattern matching in text. So we can see the usage of regex in many cases when we're filling a form, when we're filling an email field, we can see whether the field is having a particular format for the emails, which can be evaluated at runtime. And there can be many such usages for regex, right? So these are some of the example use cases for the interpreter pattern. Now let's see how this pattern is actually implemented using UML diagrams. Let's go to UML now. So this is the class diagram representation of the interpreter pattern. So we have an abstract expression with a method for interpret, right? And this will decide what is the result of this interpretation. And there can be two types of classes: terminal expression, non-terminal expression. So in our math example, the terminal expression were the numbers 5 and 3. So there is no further interpretation beyond 5, right? So that is a terminal expression. And the non-terminal expression is a composition of multiple abstract expressions. For example, the add expression is a non-terminal one. It will take in a left expression, right expression, and then the interpretation will be to add both of these items, right? So that is a non-terminal expression. So this can go down the tree and there can be multiple non-terminal expressions until we find a terminal expression to do the actual interpretation, right? So this is the class diagram representation, and the context can be anything. In our math example, there were numbers and symbols. So in the regex expression, there will be symbols like stars and carrots and things like that. And in SQL, we have the words select, insert, update, and so on, right? So the context can be anything, but the idea is to create some terminal and non-terminal expressions and use a method called interpret, which will actually interpret that expression, right? This is the class diagram. Now let's see the sequence. So there is no particular sequence actually. So the client can create any number of terminal and non-terminal expressions like this. So everything is a class, and every object will have its own instance. And then once we have everything in place, we can call interpret on the terminal expression, on the non-terminal expression, and finally we do some operation with it, right? So this is a sequence diagram. Now let's see an example for the math expression. So let's say we have three elements like this in our grammar. The first one is a number expression, which is a terminal expression, and the interpretation of this will be just a number. So it will hold a number and just return the number as it is, right? And then when we go to add expression, this is a non-terminal expression. It will hold a left expression and the right expression, and the interpretation will be to add left plus right. Similarly, subtract expression is also a non-terminal one. It will hold left and right, and the interpretation will be to do left minus right, right? So this is the class diagram representation of the math expression evaluator, right? Now let's see this in code. So I'm in VS Code now, and we have the final interpreter.cpp in our design patterns. Let's have a look. So at the top, we have the expression class, which is having a simple interpret method, which is a virtual method, which will be implemented by number expression, add expression, and subtract expression. So in the number expression, we can see in the private space, there is only one int number, and the number expression when created will take in an int value through the constructor and hold it here. And when we call interpret, it will simply return the number. There is no other interpretation for this. So this is a terminal expression. And then when we do add expression, we can see that it is holding two things: expression left, expression right. It will take both of them through the constructor. And then what is the interpretation? Left interpret plus right interpret, right? So left plus right. And then when we do subtraction, similar case, the only difference being left interpret minus right interpret. That's the only difference, right? So let's say these are our grammar rules. Let's see the usage. Let's say we are building this expression 5 plus 10 minus 3. So first we'll build the numbers using the number expression class 5, 10, and 3. Now we have three objects, 5, 10, and 3. And if we call 5-interpret, we'll get the number 5. If we call 10-interpret, we will get the number 10, and so on, right? And then let's create the subtraction, this piece here, 10 minus 3. So subtraction class will take in two things, the left operand and the right operand. So left will be 10, right will be 3. And when we call subtraction.interpret, it will go to 10 and call it 10's interpret, which will return the number 10. And then it will call the 3's interpret, which will return the number 3. And then it will perform 10 minus 3, which will be 7, right? And then we do the addition, which is 5 plus this subtraction. So we are passing in left operand as 5, right operand as subtraction, right? So far we have not called interpret anywhere. We are just building the structure. And then once we have the whole structure, we will call addition.interpret. So addition.interpret is calling 5-interpret, which will return the number 5. And then it is calling subtraction.interpret, which will internally call 10-interpret, and 3-interpret, which will just do 10 minus 3. And this will do 5 plus 7. The whole overall output will be 12, right? So there is some recursion involved here as the structure gets deeper and deeper. So let's run this and see. And the result is 12, right? So this is the code implementation of the interpreter pattern. Now let's see some trade-offs. So with the interpreter pattern, we get a great deal of extensibility. We can keep on adding the grammar rules because all the classes are independent from each other and they have their own interpretation mechanisms. So we get clean logic separation as well because the classes are separated out and then the grammar can be built to a complex state, right? Coming to weaknesses, the grammar can get quite complex with scale. So there can be more classes to deal with, more operations to deal with, and it can get a bit messy. And there is also a performance overhead as each node is a new object. So if you saw the example that we discussed, even the 5s and the 3s are all just numbers, but they have their own objects. So as the code gets larger and larger, there can be performance overhead as well, right? So these are some things to keep in mind. Okay, that's it for this video, guys. So we saw the intent, we saw some example use cases, we have discussed the diagrams, we have seen the code walkthrough, and we have also discussed some trade-offs. So if you have any inputs or suggestions, definitely put them in the comment below. Please leave a like if you found this helpful. Please subscribe to the channel if you haven't done already so that you don't miss out on any future videos. Thank you so much for watching, guys. I will see you in the next one. Cheers.